Hi guys, welcome to our BENG 4453 Computer Architecture Lecture Chapter 4, ARM Processor System on Chip, SoC. This section is about the incredible shrinking CPU. Early computers, first-generation computers, were large in size just because they just had to be. Whole rooms and specially engineered buildings were needed to house, power and cool thousands of radio tubes, size of a thumb, for a single CPU. Figure 1 shows the whole room-sized computer with thousands of radio tubes as digital logic, and Figure 2 shows the radio tubes sized of a thumb.
Second-generation computers, ushered with the arrival of transistors. This means the new transistors' development reduces the size of what had previously filled the whole rooms, now be contained in 3 or 4 cabinets the size of refrigerators. Figure 3 shows the second-generation computer, PDP-8 machine from Digital Equipment Corporation, DEC. Transistors were 1/100th the size of the tubes that they replaced and required 1/1000th of their power. The transistors were highly reliable and easier to handle and maintain than the vacuum tubes. They required much less power. These transistors replaced vacuum tubes in computers during this period.
Third-generation computers arrived with the development of integrated circuits, IC, as shown in Figure 4. By placing first a few, and eventually many, transistors on a single silicon chip, movement was allowed in 2 directions. High-end computers, mainframes, stayed physically large but increased their compute power enormously, and lower-end computers, mini computers, were smaller in size, and their price meant that smaller companies and schools could afford them. Figure 5 shows the third-generation computer with ICs. The integrated circuits were developed by interconnecting transistors, resistors, and capacitors. Integrated circuits were small in sizes, less power-consuming and less expensive than the previously switching technology. We have completed about the incredible shrinking CPU. Next section will be about microprocessor, CPU. As small as it was, the commercial PDP-8 mini-computer CPU was still spread out across several circuit boards crammed with individual integrated circuits. Intel's Federico Faggin designed the 4004 microprocessor, which became the first commercial mass-produced single-chip CPU. The 4004 is considered an oddity today because of its 4-bit data word. Its primary use was in desktop calculators. Nonetheless, it had the same memory addressing capability, 4096 bytes, as the PDP-8. The 4004 was the seed from which Intel grew its CPU empire. Intel 8008 microprocessor was introduced in 1972, 8080 microprocessor was introduced in 1973. The 8080 contained 4500 transistors, and its design influenced all successful Intel CPUs from then on. Most of those early microprocessors fell into the shadows of Motorola and Intel before 1980. The 30,000 transistor 8086, and its budget-priced sibling, the 8088, kicked personal computing into the business world with the IBM PC. The 50,000 transistor 68000 powered the first graphical user interface, GUI, computers, including the Sun and Apollo workstations and later the Apple Lisa and Macintosh. Motorola's and Intel's microprocessor architectures were competitors as they evolved, but Motorola's 68000 architecture had a difficult time competing with Intel CPUs and fell out of use by the mid-1990s. By 2006, Apple Computer was using Intel processors in its Macintosh line, and Intel became the dominant player in personal computing. By 2016, Intel's Haswell E CPUs contained 2.6 billion transistors, and the high-end Xeon server chips could have more than 2 billion. Haswell is 22nm microarchitecture first 8-core desktop processor. Intel's Knights Corner Xeon Phi supercomputer component processor contains an astonishing 7 billion transistors. Intel will release both 14nm and 10nm desktop processors for the mainstream market next year, but while the 14nm products aim for the more high-performance, enthusiast segment with 6, 8, 10 core SKUs, the 10nm products might take up the lower-end quad-core segments. We have completed about microprocessor, CPU. Next section will be about logic gates. Logic gates are important to understand because computer stores data as patterns of binary ones and zeros. All computation in digital computers is performed by logic gates, which accept one or more binary inputs and generate, usually, one binary output. The four most basic logic gates are NOT, AND, OR, and XOR. A modern complementary metal oxide semiconductor, CMOS, cell library has hundreds of cells computing a range of more complex functions that have several inputs, but at their hearts all of these more complex CMOS functions are constructed using NMOS, N-channel metal oxide semiconductor, transistors, and PMOS, P-channel metal oxide semiconductor, transistors. When a high voltage level, binary 1, is placed at the input terminal, the NMOS transistor conducts, pulling the output low, binary 0. When a low voltage level, binary 0, is placed on the input terminal, the PMOS transistor conducts, pulling the output high, binary 1. We have completed about logic gates. Now in this section flip-flops will be explained. Flip-flops are used to store a logical state which is either 1 or 0. Flip-flops are also known as where bits live. A flip-flop is an electronic circuit that stores a logical state, conventionally described as either 1 or 0. Once set to a particular state by a digital signal on an input, typically a voltage change from 0 volts to 5 volts or 5 to 0, the flip-flop will maintain that state until another input signal changes it. The D-type flip-flop is the ideal storage element for saving a state inside a computer. Because a flip-flop can store one of two logical states, it is sometimes described as bistable. There are several different types of flip-flop, but the one most used in computer logic is the D-type, where D stands for data. The ones and zeros states stored in flip-flops may be used to express computer data. A D-type IPOP takes a snapshot of the D input every time it sees a low to high transition on its clock input, a rising clock edge, and presents it on the Q output until the next clock edge arrives. The single data input, labeled DN, is used in place of the set signal, and the inverter is used to generate the complementary reset input, thereby making a level-sensitive D-type flip-flop as shown. If this data input is held high, the flip-flop would be set, and when it is low, the flip-flop would change and become reset. However, this would be rather pointless since the output of the flip-flop would always change on every pulse applied to this data input. To avoid this, an additional input called the clock or enable input is used to isolate the data input from the flip-flop's latching circuitry after the desired data has been stored. The effect is that D input condition is only copied to the output Q when the clock input is active. The D flip-flop will store and output whatever logic level is applied to its data terminal so long as the clock input is high. Once the clock input goes low, the set and reset inputs of the flip-flop are both held at logic level 1 so it will not change state and store whatever data was present on its output before the clock transition occurred. In other words, the output is latched at either logic 0 or logic 1. More reading can refer to the www.electronicstutorial.ws/sequential.sec_4.html. We have completed about flip-flops. Now in this section, shift register will be explained. The shift register is another type of sequential logic circuit that can be used for the storage or the transfer of binary data. This sequential device loads the data present on its inputs and then moves or shifts it to its output once every clock cycle, hence the name shift register. Generally, shift registers operate in one of 4 different modes, with the basic movement of data through a shift register being 1. Serial in to parallel out, SIPO. The register is loaded with serial data, 1 bit at a time, with the stored data being available at the output in parallel form. 2. Serial in to serial out, SISO. The data is shifted serially in and out of the register, 1 bit at a time in either a left or right direction under clock control. 3. Parallel in to serial out, PSO. The parallel data is loaded into the register simultaneously and is shifted out of the register serially 1 bit at a time under clock control. 4. Parallel in to parallel out, PPO. The parallel data is loaded simultaneously into the register, and transferred together to their respective outputs by the same clock pulse. We have completed about shift register. Now in this section, instruction inside the CPU will be explained. An instruction is represented in memory by a binary value some number of bytes long. On many 32-bit CPUs like the ARM11 in the original Raspberry Pi, this number is 4 8-bit bytes. The Raspberry Pi 4 uses the same instruction set in use by the Raspberry Pi Model 3. Its SoC is made up of 464-bit Cortex-A7 2 cores. Within this binary number are encoded the identity of the instruction, called operation code, or opcode. 1 or more operands, which are values or addresses associated with the instruction. A binary machine instruction is loaded from memory into the CPU, where the CPU decodes it, takes it apart to determine what must be done, and then executes it, during which the actual work of the instruction is accomplished. When an instruction has been dispatched for execution, it's said to have been issued, and after it is completely executed, it's said to be retired. When the current instruction is completed and retired, the next instruction in the program is loaded into the CPU for execution. Next section is about what happens inside the CPU during a program execution. Program execution by the CPU works like: firstly, the CPU fetch the first instruction on the program. Next, the address of the first fetch instruction from PC is loaded the address register during the first clock cycle. PC is a pointer pointing to an address location where an instruction is to be fetched and place the instruction into instruction register, or sometimes is also known as current instruction register. After the instruction is loaded and hold into the instruction register, then the instruction is transferred into the decode unit to decode the instruction. After decoding the loaded instruction into the decode unit, the instruction is then loaded into the execute unit for execution. During the execution of the instruction, the internal register of AC content is set to constant value 0. And so on, for as many instructions as are in the program. The program counter is a pointer inside the CPU that contains the memory address of the currently executing instruction. Machine instructions do things like 1. Add, subtract, multiply, or divide. 2. Perform logical operations like AND, OR, XOR and NOT on binary values. 3. Shift a multi-bit binary value to the left or right. 4. Copy data from one location to another. 5. Compare values against constants or other values. 6. Perform CPU control functions. In modern CPUs, separate subsystems execute different groups of machine instructions. One arithmetic logic unit, ALU, handles simple integers such as maths and logical operations. Example shows, an 8-bit data A is added with 8-bit data B. The ALU performs the addition of these two data. The addition result is stored into X location. In modern CPUs, separate subsystems execute different groups of machine instructions. Floating point unit, FPU integrated circuit, which handles all mathematical operations that have anything to do with floating point numbers or fractions. It is a dedicated logic unit specifically designed to work on floating point numbers and nothing else. Single instruction, multiple data, SIMD, unit handles vector maths that performs operations on multiple data values at once. This type of maths is essential in audio and video application. It describes computers with multiple processing elements that perform the same operation on multiple data points simultaneously. We have completed about instruction and inside the CPU. Now in this section branching and flags will be explained. Branching is important as an ability of a program its course of execution depending on the results of its work. The branch instructions, which have the power to skip forward or backward in the sequence of machine instructions that make up a program. Branch instructions can be categories into unconditional branch instructions and conditional branch instruction. This is called conditional branch instruction. In the example, when x plus y is more than z, the condition is true, then the instruction branch to x plus equals y and exit. Otherwise, the x and y more than z is exited when it is false. A conditional branch instruction combines a test of some sort with a branch. These tests generally involve a group of single-bit binary values called flags that are stored somewhere in the CPU, generally in a group called the flags register or status word. If A smaller than data, then carry flag C is set. If A is equal to data, then 0 flag Z is set. If A is larger than data, then carry C and 0 Z flags are reset. We have completed about branching and flags. Now in this section the system stack will be explained. A stack is a last in first out, LIFO, data storage mechanism essential to the operation of most modern CPUs, including the Raspberry Pi's ARM11. Or also, the stack is a segment of memory where data like your local variables and function calls get added and / or removed in a last in first out, LIFO. The key characteristic of stack operation is that data items are removed from the stack in the reverse order of how they were stored. When you compile a program, the compiler enters through the main function and a stack frame is created on the stack. One stack frame on the stack that holds the main function, along with the local A, B and some variables. After using the printf function, the created frame along with the local variables are only accessible in memory for the duration of the frame, are no longer accessible after returning the 0 value from the function. In a computer system, a stack is an area of memory set aside for LIFO data storage and managed by machine instructions designed to implement the stack data structure. Figure 4-6 shows a simple stack. The stack begins at a location in memory specified by a base pointer. A pointer is simply a memory address. After it's loaded with an address, the value of the base pointer doesn't change. A second pointer, called the stack pointer, indicates the memory location to be accessed next. It's sometimes called the top of the stack. To add an item to a stack, the stack pointer is first incremented so that it points to the next available memory location in the stack. The data item is then written to that location. Informally, this is called pushing an item onto the stack. To remove an item from the stack, the item at the top of the stack is first copied to a register or some other place in memory, and then the stack pointer is decremented so that it points to what had previously been the top item on the stack. This process is called popping an item from the stack. If you follow the 4 stack snapshots in figure 4-6, you can see how the stack grows or shrinks as items are pushed onto it and popped from it. In figure 4-6, the items at the top of the stack are shaded. Stacks are useful in that they can manage nested subroutine calls made from within subroutines. Each time a new nested subroutine call is made, another layer of data and return addresses is added to the stack. Stacks are used for temporary storage of both data items, often register values, and memory addresses during subroutine calls. A subroutine is a sequence of actions in a program that is executed as a group and given a name. Anytime the subroutine's actions need to be executed, some other part of the program can call it, meaning transfer execution to the subroutine until the subroutine's work is finished. Then the subroutine returns execution to the part of the program that called it. In programming languages like C and Python, subroutines are called functions. Everything that goes on inside a sequential circuit like a CPU is synchronized to a pulse generator called the clock. Each pulse from the clock triggers a clock cycle, during which the CPU does some specific work. Addresses is placed on the address bus during the positive edge triggered. The memory address register, MAR, will fetch the address from the program counter, PC. Then PC is incremented. Then the instruction is decoded at the decoder unit before execution. After completion of execution, data is sent to accumulator register. We have completed about system clock and execution time. Now in this section microcode instruction will be explained. Figure 4 to 7 shows how this worked on early computers that had slow instructions due to microcode. The use of microcode forced some instructions to take more clock cycles to complete than others. In the example, Instruction 3 takes more cycles to complete the instruction than others. By 2000 the chart of machine instructions versus clock cycles changed to something like figure 4 to 8. Sufficient transistors able to execute all instructions in almost the same time amount. We have completed about microcode instruction. Now in this section pipelining will be explained. Pipelining, a standard feature in RISC processors, is much like an assembly line. Because the processor works on different steps of the instruction at the same time, more instructions can be executed in a shorter period of time. The following 5-stage example assumes a load-store RISC architecture. Instruction fetch: if fetch instruction from memory, cache. Instruction decode: ID decode instruction and read operands which must be in registers as this is a load-store machine. Execute: execute the instruction or, if it is a memory access instruction, read or write, compute the memory address. Memory access: MEM memory read/write. This is a no-op stage for instructions that do not access memory. Write back: WB write results back to registers. Let's say that there are 4 loads of dirty laundry, A, B, C, and D, that need to be washed, dried, and folded. The first load is placed into the washer for 30 minutes, dry it for 40 minutes, and then take 20 minutes to fold the clothes. Then pick up the second load and perform wash, dry, and fold, and repeat for the third and fourth loads. Suppose the wash, dry and fold started at 6 p.m. and worked as efficiently as possible, the laundry would be continued until midnight. However, a smarter approach to non-pipelined problem would be to put the second load of dirty laundry of task B into the washer after the first wash of task A was already clean and whirling happily in the dryer during the second cycle of task A. Then, while the first load is being folded, the second load in task B can be dry, and a third load in task C could be added to the pipeline of laundry while folding the clothes of task B. This method can be continued till completion of task D. Using this method, the laundry would be finished by 9:30. How much overlap you can create in a given CPU depends primarily on how many stages a CPU's instruction execution can be broken down to. During early architecture 3 and 4 stages instruction pipelines were state-of-art. Raspberry Pi has 8 stages instruction of pipelines. The current Intel processors have pipelines with 20 stages or more. Moving instructions through the pipeline at a continuous, uniform rate is crucial. Certain things can disrupt the smooth flow of instructions through a CPU pipeline. These are called pipeline hazards, and they can lead to delays in the pipeline. The delays are called pipeline stalls. A pipeline stall is a delay in execution of an instruction in order to resolve a hazard. There are three general categories of pipeline hazards. Control hazard, caused by conditional branch instructions. Data hazard, caused by data dependency between instructions. Structural hazard, caused by resource conflicts. If the first instruction shown in the pipeline is a conditional branch instruction, and the logic that resolves whether a branch is taken is located in the execution X stage, you could end up branching away from sequential instructions that are already in the pipeline and have been fetched and decoded. In simple words, control hazard occurs when next instruction cannot be fetched while initial instruction is branch away. Because the initial instruction is not completed from the branching and there is no outcome. Data dependence is more subtle. Suppose the result value from one instruction is needed as an operand by the next instruction in the pipeline. The second instruction may require the value before the first instruction has finished generating it. So if second instruction is preceded with the required value from instruction through the pipeline, it would end up using a value that is garbage or a leftover from some earlier calculation. Structural hazards is resource conflicts happen when two instructions in the pipelines need to access some CPU resource at the same time, T=1s. For example, if two instructions, instruction A and instruction B, in different pipeline stages need to access external memory via the cache system at the same time, one of these instructions must take priority over the other. The general approach is for the instruction decode logic to identify when a hazard is about to occur in the pipeline. The hardware that performs this check is referred to as an interlock. If a fetched instruction represents a hazard of any kind, a bubble is inserted into the pipeline ahead of the problematic instruction. This generates a delay that allows earlier instructions to finish what they're doing before they conflict with instructions coming up the pipe. We have completed about pipelining. Now in this section ARM11 pipelines will be explained. The pipeline in the ARM11 CPU is divided into 8 stages, as shown in Figure 4-12. In addition to the pipeline being divided into 8 different stages, there are 3 possible paths, A, B, and C, through the pipeline. Which path the execution takes depends on what type of instruction is executing. The first 4 stages are identical, regardless of the instruction. However, when the instruction is issued, the decode logic chooses one of the 3 possible paths. Each category of instructions has its own pipeline path. Integer execution path, for most instructions that execute integer operations. Multiply accumulate path, for integer multiply instructions. Load/store path, for load and store instructions. We have completed about ARM11 pipelines. Now in this section superscalar execution will be explained. A superscalar processor can execute more than one instruction during a clock cycle by simultaneously dispatching multiple instructions to different execution units on the processor. A superscalar CPU fetches two instructions from memory and examines them to determine whether they can be run in parallel. If so, the CPU parcels out execution of both instructions to dual execution units. The execution units handles the work of the instruction only and specialize in integer maths and logic, floating point maths and vector maths. Single instruction, multiple data, SIMD, describes computers with multiple processing elements that perform the same operation on multiple data points simultaneously. As it can be seen, 4 operations are performed with one single instruction, but the principle is the same. A vector of 4 values is loaded from memory into registers. In some computer architecture, a single SIMD instruction performs 4 operations: addition, subtraction, multiplication, and division, at once, in parallel. Then the entire vector is written back to memory. We have completed about superscalar execution. Now in this section endianness will be explained. In computing, endianness refers to the order of bytes, or sometimes bits, within a binary representation of a number. Endianness can be categorized into big endian and little endian. Big endian. Data from LSB is stored into higher memory location. Data from MSB is stored into lower memory location. Little endian. Data from LSB is stored into lower memory location. Data from MSB is stored into higher memory location. Thank you. We have completed Chapter 4 on ARM Processor SoC. If you have any questions, do not hesitate, contact me.